Good afternoon. Can you all hear me? Yes, perfect. Okay. I want to welcome you all to this fourth and last session here today in the Sustainability and Innovation theme. This session is called Zero Footprint Geothermal. My name is Hulda Kristín Helgadóttir, and I will be your moderator here today. I'm pleased to see all of you interested in the topic, and I'm also very interested to hear. We have coming up 5 speakers from all around the world. We have one from New Zealand, one from the US, and 3 here from Iceland. And they're going to talk about carbon neutrality in geothermal energy production, and also how it is a key foundation in the transition to clean energy. The session will also dive into emissions blueprint, the life cycle assessment of a geothermal power plant, how geothermal can reach net zero, and how can issues caused by air ingress into the gas stream be managed successfully. But before we start, I would like to inform you that we're going to hear all 5 presentations at once, and they will have around 10 to 15 minutes to give their presentation. After the last speaker has presented, we will invite them up here to the panel or to the cozy sofas, as you can see here, and we will have a short Q&A session if time allows. But now I would like to invite the first speaker up to the stage, Mr. Kenneth McIntosh. He's an engineer and the president of Trimary Corporation. He will tell us about managing issues caused by air ingress into geothermal non-condensable gas when capturing CO2. Welcome, Ken.
Thank you, Hulda. So to start off this session where we're going to talk about carbon neutrality, I'm going to give you a little bit of a safety talk to start the session. And that the topic here is managing the issues of air ingress in non-condensable gases. The non-condensable gases are removed from the condenser system in flash and dry steam type geothermal plants. They contain CO2, that's what we want to capture, and there's a lot of it generally, but also hydrogen, H2S, methane, and ammonia, among other species. Air gets into the non-condensable gas due to the vacuum conditions in dry steam and flash power plants. Now you have air and fuels, namely the hydrogen, methane, are probably the chief among those, sometimes H2S. When you capture CO2 from this stream, you remove the diluent, so you've concentrated now the air and the fuels. And so that's the reason I want to raise this as a safety topic, to make sure that people capturing CO2 or designing new plants don't have an issue with flammable species. On the screen here we have 2 simple examples of geothermal plants. On the left is a simple binary. The geothermal fluid comes out of the well. It's generally single-phase water, passes through an exchanger where it exchanges heat with a second fluid and goes back down. No non-condensable gas here, no issue. If we look at this simple single-flash power plant on the right, the geothermal fluid comes out of the well. It's 2-phase. We take the steam through the turbine and condense it under a vacuum, and then those species that I mentioned that won't condense exit via a non-condensable gas removal system. The issue here is that when you have a vacuum, it's generally almost impossible to seal off all the leaks, so air leaks in. Secondly, if you have a direct contact condenser like shown here, the water coming from the cooling tower is going to be saturated with air, and that's going to come out in the condenser as well. What that results in is air in your non-condensable gas up here. Okay, so if you're going to capture CO2, that's commonly done by absorbing the CO2 into a liquid, leaving behind the other species. A couple of examples are given up here on the screen. After CO2 removal, the non-condensable gas stream consists then of some residual CO2, nitrogen, oxygen, so air, hydrogen, methane, etc. These species are at higher concentrations, so that can result in a flammable gas mixture, the reason for this talk. So let's cover a few flammability terms. First off, combustion requires both oxygen and fuel. So looking at the oxygen first, there's a term called limiting oxygen concentration, or LOC. It may also be called minimum oxygen concentration, or MOC. They mean the same. And it's the minimum amount of oxygen that has to be present for a combustion to occur. Looking at the fuel side, there are two terms. The first is lower flammability limit, or LFL, also sometimes called lower explosive limit, or LEL. And that's the minimum amount of fuel that has to be present in order for there to be combustion. Similarly, on the high end of the fuel, there's the upper flammability limit, or UFL, also called the upper explosive limit, or UEL. They mean the same thing. And that's the maximum amount of fuel. If there's too much fuel or too little fuel, it won't burn. In between, it will. So, the last term we'll define is an explosive gas mixture. This is a gas that's in its flammability envelope. That is, it's above the limiting oxygen concentration and between the LFL and the UFL. In this condition, a source of ignition will allow the stream to burn, deflagrate, or explode. This is what we want to avoid. Okay, this shows another flash or dry steam type plant. The steam's coming into the turbine. There's the main condenser. This is where the vacuum is the lowest. And then there is a gas removal system shown here with the non-condensable gas coming out, passing through a CO2 capture system that has upstream H2S abatement. The streams in red are the primary ones to be concerned about, and that includes the CO2 product stream sometimes. For example, if you're going to purify the CO2 stream and you distill contaminants out of it, you may get enough oxygen out of the CO2 stream to cause a problem. So, what does this look like? If there was no air ingress, the stream would look like what's shown here in the second from the left column. No air, no problem. After the condensing system and the non-condensable gas removal system, it looks like this, and now we have 3.2% air. A good portion of that came from the cooling water, but some came from leakage. And this is a theoretical example, but it's not too far off. We can calculate, or estimate, I should say, the limiting oxygen concentration, and that's estimated at around 7.7%. We can apply safety margins, which would say, depending on which one you used, you need to be below 5.7 or 4.6. We can see 3.2 is below both of our safety margins, so we're in good shape. No problem with the stream. Now, what if we capture 90% of the CO2 out of that stream? This second from the left column is the same stream we saw on the last page. We've removed 90% of the CO2, and here's the new composition. Note that the oxygen is now at about 10%. And the total fuels and inerts, which is the value used in the calculations, is around 53%. So now we have a stream that's above the limiting oxygen concentration and between the two flammability limits. So this stream is dangerous. It could burn, deflagrate, or explode. This is what we need to be careful of. Sometimes avoiding forming a stream like this will perhaps limit the CO2 capture. You may have to limit it to, maybe it's 85%, for example. So what do you do about that? The number one thing is to minimize oxygen ingress. This means fixing vacuum leaks. There are methods to detect them. You need to have a periodic program to go around and find and fix the leaks. Second, do not put gland steam leak off into the main condenser. This can be a large source of air into the non-condensable gases, so that should be routed elsewhere. You can potentially do something with direct contact condensers. Perhaps if you're over-circulating, you could turn the cooling water back down. That'll reduce your oxygen proportionally. You could dilute the residual non-condensable gas, potentially. Might be expensive, but there are approaches that could be applicable there. You could use online monitors, for example, for oxygen to give you some warning, give your operators warning that something has changed in the system and they might be approaching a dangerous condition. Those are the primary things one would attempt to do. This last one is, if all else fails, you could design for an explosive gas mixture to handle that. There are designs in other industries. Here's an example of a vent system where the gas coming in is an explosive gas mixture. So it can be done, but you don't want to. You really want to prevent the problem in the first place. Okay, so in conclusion, yes, CO2 can and is being captured from geothermal non-condensable gases from flash and dry steam plants. However, please be aware of the possibility of both fuels and oxygen being present, especially when capturing the CO2. You may concentrate them. You need to train your geothermal operating staff about the potential issues so that they don't inadvertently wander into a region where they might create an explosive gas mixture and have a problem. You need to incorporate measures to reduce oxygen ingress. This is the number one thing you can do from an operating practice. It would be good to implement operating procedures, safety devices, and equipment design changes to minimize flammability concerns. And lastly, for new plants, account for the fact that you're going to want to capture CO2 at the beginning and design the plant so that you avoid these kinds of issues. And thank you for listening to the Safety Talk.
Thank you, Ken, for this very interesting presentation and good timekeeping. We are on schedule. And we're going to hear more about how oxygen is actually very important here later on in the session. But next, I would like to invite to the stage Elín Vignisdóttir. She's a geographer at Verkís, and she's going to be presenting to us the life cycle assessments of geothermal power plants in Reykjanes and Svartsengi. Welcome to the stage.
Well, good day, everyone. So happy to see so many of you here. I'm going to be talking about, I work a lot with sustainability in my work, among others, life cycle assessments. And I'm going to be presenting this, how we have been approaching this in the geothermal sector, and give an example from a large studies we did for HS Orka on the power plants in Reykjanes and Svartsengi. So life cycle assessment is this methodology that we have for assessing environmental impacts associated with all stages of the life cycle. It's a tool to quantify these environmental impacts that we're having. And we're not looking only at the impact we're having locally, but over the whole life cycle. So for a power plant, for example, you're looking at the materials you use to build it, constructing it, the operation, and then the end of the life scenario, if you're going to tear it down and throw it away, or if some of it re-enters the stream via recycling. And it's a highly standardized method today. I see life cycle assessment as an important tool in the geothermal sector as well as in other sectors. We can use it to calculate the carbon footprint of the power production as well as other environmental impacts. But we can also use it at a more high level or component-based during the design of a power plant. Since we are quantifying the environmental impacts, we can highlight these hotspots during the life cycle where we can reduce our impact. And we can also use it at a more of a component level while comparing design solutions. And that we have done like mini life cycle assessments on different solutions to compare them, and then you have a way of including environmental impacts in your decision making. The results from a life cycle assessment can be quite applicable. You have quantified the impact you're having, such as the carbon footprint, and you can communicate this then to your stakeholders and to the wider world. We're seeing producers making environmental product declarations where they are communicating their impacts. You could use the results in your sustainability reporting or a sustainability certification, but increasingly also statutory bodies are requiring this kind of information, such as the environmental European Union with their taxonomy regulations, whether your activity can be qualified as sustainable or not. And this is probably happening in more places around the world, also in procurement or funding, that you show how you are impacting the environment and how sustainable you are. Yes, I'm going to take an example from these two geothermal power plants. We did separate studies on them, where the aim was to analyze their environmental impact with focus on carbon footprint. And the end goal was to see if it fulfills the EU taxonomy requirement. This is the location of those two power plants in the Reykjavik Peninsula. And we have the eruption going on somewhere around here, so really close by. These power plants have both been in operation for some time. The Reykjanes one started operation in 2006 and was expanded with 100 megawatts and was expanded. I think they started operation of the expansion last year. And Svartsengi is an older one, which was established in 1978. And they are in the middle of doing an expansion to it. And both of these, Svartsengi is selling combined heat and electricity, while Reykjanes is selling electricity, but selling their thermal seawater as well as a byproduct. So this was included. Some definition of our study, we were only calculating the environmental impact of global warming potential. So, for 1 kilowatt of energy, the combined electricity and heat. And we calculated this over a 30 years lifetime. And then these results were verified by an independent third party. Doing an LCA, you need to define your system boundary. That is to say, which components of the product, or in this case, the geothermal power plant, are taken into account in the calculations. And here we are looking at the construction and resources phase, then the operation of the power plant, and then the end of life. And directly to the results, our calculation shows that for both power plants, they were within the limit that EU taxonomy has set out. For Reykjanes, it was around 17 grams per CO2 per kilowatt hour. And for Svartsengi, it was a bit higher. It was 43.5 grams CO2 per kilowatt hour. And for both studies, the major contributors to the carbon footprint were these 5, with direct emissions by far the largest, since we have to include the direct emissions from the wells in the LCA study. If we exclude the direct emissions, then we have the energy use of the power plant, the wells, that is to say, both drilling and coping, and then earthworks and machinery. What I want to talk more about is the challenges we faced. Some of them are related to the lifetime, because these are older power plants that have been in operation for some period of time. For Reykjanes, it was simpler since it started operating in 2006. But for Svartsengi, we had a problem since it's almost 50 years old. So where do we place this 30-year time frame? After much discussion and consulting with other experts, we decided that we would include everything that is part of the power plant that is needed for power production today. So we could exclude everything that had been decommissioned. So therefore, we set the time date around the year 2000. Another thing related to the lifetime was that, as Svartsengi showed us, that the lifetime of a power plant can be much longer than 30 years, as was stated in the guidelines we were following. And most other LCA studies on geothermal are using 30 years as a study period. So, but Svartsengi is almost 50 years old and still in operation. So the end-of-life scenario, we decided to address that the power plant would not cease to operate and be torn down, but we would renew all major machinery for the electricity production, maintain the buildings, and then gain from the recycling of metals from the equipment. We also did a sensitivity analysis on the life cycle, and that showed us that the carbon footprint, it decreases with time, but then it kind of reaches a low and it starts increasing again. For Reykjanes, this was around 60 years, and then the carbon footprint was about 10% lower, but then it started increasing again. And it showed us that at that low point, you have to increase or optimize the energy production to keep the carbon footprint low, such as by adding new wells. The data was also an issue since, like for Svartsengi, it was quite old and data not readily available. So this was our approach, was to do a quality check on the data. We put an emphasis on having high quality data for the major contributing elements, such as the direct emissions. For the direct emissions, we have measurements from the wells. And also for the drilling of the wells, we were cooperating with HS Orka and the contractors who are drilling to get as correct data as possible. But for other areas, we had to make certain assumptions, but then we used a sensitivity analysis on our assumptions to make sure that they were not impacting our results. And we could say that even though some data had low quality, it was not impacting our end result. And lastly, issue that was quite discussed are the direct emissions, because they are the largest contributor to the carbon emissions from the power plant, but emissions of CO2 are also coming from the geothermal field, or from the earth around us, and these emissions vary quite a lot and are hard to measure. And the question is, do we include all the emissions coming from the wells as emissions from the power plant? Or can we say that it's a surplus? Or can we extract the natural emissions occurring? I think that here could be a really interesting study to do. And I know my colleague who's speaking after me is going to address upon this. But to conclude, I think LCAs are a powerful tool to better understand the environmental impacts of geothermal power. We can use it to map out where our impacts are happening, and it gives us an opportunity for enhancing the sustainability of geothermal power plants. Thank you.
Thank you, Elín. Really interesting presentations, and I hope we get the time to ask questions later on about the methodology. And good you touched upon a later session that's coming up. But yeah, and I also wanted to remind you that we will have the questions in the end. So please, if you have any questions, try to memorize or write them even down so we can have a nice and successful session afterwards. But next up on stage, I would like to invite Sigurður R. Rúnarsson, a specialist in power plant operations at OnPower. His topic is on target for net zero, making geothermal power plant carbon neutral. Welcome to the stage.
Thank you. Good afternoon. Thank you all for coming. I'll be talking a bit about our CarbFix process, what we're doing in carbon capture and storage at Orkunáttúran or OnPower. I'll tell you a bit about the history of the carbon capture and storage operations at Hellisheiði. The Silverstone project, which is a project that is intended to make Hellisheiði power plant almost carbon neutral by itself, and I'll tell you a bit about the operational challenges that we've had to face. This is Hellisheiði power plant. It's a flash steam power plant with an electrical capacity, nameplate capacity of 303 megawatts. And we also produce about 200 megawatts thermal used for district heating in Reykjavík. And I'm going to start by talking about a gas that is not CO2 but H2S, because when we started our power plant in 2006, when Hellisheiði started operating, people started to observe increased H2S levels in Reykjavík and the surrounding area. And this pollution was traced to the power plant, and it, in some cases, could get so bad that it was above the limits for public health. So we had to take some action. So at this time, CarbFix was already a research project at Reykjavík Energy with very promising results in capturing and mineralizing CO2 in strata And basically, at the risk of oversimplifying, somebody basically asked, the things we're doing to CO2, can't we do the same to H2S? And basically we could. We built a pilot plant in 2010, or operated a pilot plant in 2010 to 2012. Ingve can correct me if I'm... and that showed that H2S was mineralizing just fine along with the CO2. So we built our gas abatement plant, which we started to commission in 2014, with the goal of reducing H2S pollution. But it also, of course, had the benefit of capturing CO2. Originally, we captured about a third of the H2S and 15 to 20% of the CO2. And then when we expanded the plant in 2017, we doubled the capacity up to its current capacity of 12,000 tons of CO2 and 9,000 tons of H2S, which, as you can see, is a third of the CO2 and almost 3/4 of the H2S. And H2S levels in Reykjavik are within limits most of the time. But as time went on, and we set our climate goals, we decided to go all the way, basically, and we wanted to make Hellisheiði power plant carbon neutral. So with the assistance of the EU, with a grant of 3.9 million euros, OnPower and Carfix started to design and build a new capture plant capable of capturing and storing 95% of the CO2 emissions from Hellisheiði. And this project alone will deliver 10% of the emission reductions for energy and industry called for by the Iceland's Climate Action Plan for 2030. So it's kind of a big deal. Here you can see the old plant, and right next to it, we've started building the new one. And just to tell you really quick and dirty about the process, we basically take the non-condensable gases from the turbine condensers. We send them to a scrubber where they are, those gases that dissolve in water will dissolve. And the water is then pumped back into the geothermal reservoir, where it will mineralize the CO2 as calcite and the H2S as pyrite. The new plant, as you can see, will be run in parallel and has more or less the exact same process, with some iterations, of course. And of course it has triple the capacity. And will hopefully be started up before the end of this year, and will enable us to capture 34,000 tons of CO2 and all of the H2S that we're getting out of our process. So here you can see them side by side. We basically built another one, just a bit bigger. And I'm going to tell you a few things about what it's like to live with. The old plant was intended to reduce H2S pollution especially during unfavorable weather. But now the priorities obviously have shifted towards carbon neutrality, so we will need to put more effort into keeping things running smoothly. When we were only thinking about the H2S pollution, it really didn't matter if we shut it down, even for a few days or a few weeks, if the weather was favorable. But now we have a goal, a climate goal, which we are going to try and reach. Here you can see the composition of the gas stream, which is supplied to the gas abatement plants. As you can see, it's mostly CO2 and H2S, but with quite a lot of hydrogen and some other stuff thrown in. And as Ken explained very well to us, we need to keep the oxygen out of this mixture. Obviously, by as Ken explained, keeping the gland steam leak-off separate, having the vacuum system airtight, checking for vacuum leaks, and monitoring O2 concentrations in the gas stream. We have to keep the gas flowing. The big thing here is compressor maintenance. Here you can see the liquid ring compressors in the old station. There's 2 of them. There will be 2 of them in the new one. And these are the beating heart of the system. Without them, we are at limited capacity, so we have to keep them running smoothly. Luckily, these have been quite stable, quite a comfortable operation. In fact, we've had some trouble with the gears, but the new compressors are gearless, so that won't be a problem. And we have to keep the reinjection system at a stable pressure. If we don't, we will get gas bubbles in the system, which can clog the reinjection, stop everything from flowing, because it's basically a large soda stream machine, and it works both ways. You can put the gas in by pressure, but if you release the pressure, it comes right back out again. So it has to be pressurized all the way into the reinjection into the well. Then we have to keep the water used to dissolve the gases at a cool temperature between 10 and 12 degrees, because without that, when the temperature rises, the water is better at absorbing, at dissolving the gases at a lower temperature. Just to recap, OnPower is building a new gas capture plant based on the CCS process from Carbfix at Hellisheiði, which will make the power plant very close to carbon neutral. We have to take care of the gas composition because the gases can become flammable and explosive, as we have learned. And the system as such is not terribly difficult to operate, but of course needs care and attention as other things. Thank you.
Thank you for the presentation, Sigurður. It was nice to hear how you're gonna reach carbon neutrality at Hellisheiði power plant. And next, I would like to invite up to the stage Ásgerður Sigurðardóttir, a specialist in geothermal operations at Landsvirkjun. Her topic is regarding the monitoring CO2 Geothermal emissions in volcanic environments. Welcome to the stage.
Thank you for the introduction, Hilda. I hope you're all having a wonderful conference. So, in my talk, I want to bring a bit of food for thoughts in the counting of CO2 emission in active volcanic systems. As all our geothermal high temperature geothermal systems are located in these volcanic active systems and on the plate boundaries. So the outline of the talk, it works, yes, is what have we learned from Krafla, what have we experienced in Þeistareykir, the general CO2 hypothesis, and then have a discussion on and conclusion. And of course, first there is Krafla. So Landsvirkjun operates 3 geothermal power plants in northeast. Am I able? Yes, over there. And just few days ago, our Víti crater became 300 years old. Big birthday, and that happened on 17th of May. Yeah, and that marks the beginning of the Mývatn fires when Víti was formed, with a huge explosion, and this was in 724 and lasted for 5 years. So, and because of these old records, we know that the area around Víti has been constantly changing with erupting mud geyser, blue hot bubbling water ponds, active steam geyser south of Víti. 1944 there was a new active steam crater that was discovered. And then in the 70s, there was a volcanic episode that took place. So a dynamic system. Krafla high temperature geothermal system lies in involved volcanic complex involving caldera and a large cooling magma chamber. And it has been active for more than 100,000 years. And it was formed in a violent eruption and has been active with recurring volcanic episodes. These beautiful pictures we have here, we can see the location of Víti in the middle of the photo, and in the back of it you can see the Krafla volcano. So Víti, which means hell, so we have our own astonishing hell in the north. Yeah, so the closed ellipse shows the main natural outflow of the CO2 in the area. And this is the location of the wells which have the highest CO2 concentration. You might think that this picture was taken yesterday at Reykjanes, but no, this was taken during the volcanic eruption within Krafla caldera. And during the Krafla fires, there were at least 18 magma intrusion events. And here on this graph, you can see how the elevation changes through these intrusion events. With a single rifting and deflation events varied from few centimeters to 2.3 meters. Here you can see the changes and the variation in CO2 content in the 2 geothermal wells in Krafla, measured in weight percent of the total flow. So accompanying the land elevation, these volcanic tectonical activities had a major impact on the geothermal fluid chemistry of the area, with high fluxes of volcanic gases, especially in CO2. And the amount of the non-condensable gases increased from lower than 1% up to peaking up to 6% here. So there was a big part of the Krafla area that was affected by this gas contamination and was non-explodable for a few years. And it wasn't until 1994 that the area had degassed and the gas content had dropped below 2%. And then the whole area was fully explodable. But still we have a relatively high CO2 in wells close to Viti. Here you can see the emission in Krafla. This is in grams per kilowatt hour. And you can see that at the top here during the Krafla fires. So the power plant was started production in 1977. And the CO2 peak is rising there. And in 1999, there was another peak, and that was due to commissioning of the second turbine unit. And today, the emission is around 57 grams per kilowatt hour. That's a different scenario versus 300 grams. So, our experience from Þeistareykir. Þeistareykir volcanic system is the northernmost active volcanic system on land in Iceland. And the most recent eruption there was 2,400 before present. And the heat source is dominantly thought to be the intrusive activity. In Þeistareykir, you have significant surface activity. And in terms of CO2 emission from the power plant, there's a constant trend, relatively low, but monitoring of natural gas emission shows a great variability at this stage. So, to be fair, so there has been research in Þeistareykir for up to 40 years now. But since 2015, there has been quite extensive survey of emission from soil done by Iceland Geosurvey in the area. And we can see the great variability since this Þeistareykir power plant started operating in the autumn of 2017. And the whole line, you can see here, with the arrow bars, shows the total emission from soil in the geothermal area. And that was done with a closed chamber method with spot sampling. And then the broken line shows the CO2 emission from the production from the geothermal wells over the years, whether they were producing or exhausting. And the emission shows you it's quite constant. And it varies from around 22 tons per day of CO2 down to 15. And it was quite a bit in the beginning because of there were exhausting wells that hadn't started producing. But on the natural emission, that varies from 291 tons, and now it is around 135. But this graph can be interpreted in many ways. One could be that the natural emission is very variable, and it can be due to natural emission. It can be weather, it can be groundwater, or other things. Or that the production has reduced the flow of steam, for example, to surface, where it has taken to the production wells instead. But at least the emission from the production roughly fits into the kind of the error bars. So on the hypothesis on the origin of CO2 in volcanic systems, the heat source of many of these systems are likely to be magma intruded into the roots, intrusion, deep crustal or mantle source. In Iceland, big part of the magmatic gases, for example CO2, enter the reservoir from below impulses related to the intrusion. And then also that depending on the bedrock in the sites of the resource, if it's carbonated bearing rock, the emission can also increase temporarily. In many areas, the gas content of the CO2 follows a gas mineral equilibrium, but in Krafla and Þeistareykir, in many of the sites, they do not, as Krafla shows the necessary of having an external CO2, magmatic origin, and for Þeistareykir shows a lower CO2 emission than expected, considered to be insignificant supply of gas, for example, that the intrusion has already been degassed in terms of CO2. So, in regard on the long-term CO2 natural cycle, volcanic geothermal systems are a part of the carbon cycle, and they interact with this carbon cycle in a complex way, involving both the release and sequestration of the carbon. And here in Iceland, we are located on this plateau that's on the ocean ridge. So on this photo, you can see the location of active volcanoes around the world, and these areas have a vast potential to contribute to global energy. So, on the conclusion, who is responsible for the CO2 emission in volcanic geothermal fields? So the origin of the CO2 in volcanic systems can be complex. No two sites are the same, and a substantial part of the CO2 is of magmatic origin. In some cases, there is a high uncertainty in, if any, that CO2 is caused by geothermal power generation. That is depending on the time factor. But more work needs to be done to map the emission. And if companies are responsible for the CO2 emission from volcanic geothermal sites, it has to be based on solid and accurate information. No room for uncertainty or vague assumptions. So it's crucial that the regulation framework and public policy do not disadvantage geothermal power generation beyond the renewable energy source. So because this is not, that would not be beneficial for the climate actions. So here we have the Krafla area, and that is that. Oops. Thank you so much, Ása. It was really nice to see the site, and I hope some of you are going to the post tour to Þeistareykir, and you will be able to visit Krafla and Þeistareykir. Hopefully. And finally, I would like to invite to the stage Dr. Eileen Kaya, a senior lecturer at the University of Auckland. Her topic is regarding the carbon neutrality in geothermal energy production, a blueprint for emission-intensive sectors. Welcome to the stage.
Thank you. Kia ora, everyone. Can everybody hear me? Because I'm a bit shorter than others, so it might take a bit longer. So yeah, Eylem Kaya from the University of Auckland, and my presentation is also going to be about carbon dioxide. So New Zealand is taking significant steps to address the climate change, and geothermal industry is also started to contribute. Although our this is not my most recent presentation, but okay, anyway, I'll try to make it So New Zealand is taking significant steps, and geothermal industry also contributing to eliminate their intensive emissions. Although New Zealand geothermal power stations doesn't really release too much carbon dioxide, but still they started to gradually decrease their CO2, and so if you can see from the slides, in Nafa, Te Huka, and Ngatamariki, geothermal fields are actively injecting their carbon emissions. And at the University of Auckland, myself and my colleague, we received a grant from the government, $6 million for the next 5 years, and we are going to be working on this problem as well. So the aim of the program is actually to create a process that can store the carbon dioxide in the mineral form, in the solid form, and at the same time support the reservoir pressure as well to enable higher energy production. The scope of the project is first enhance the solubility of the gas inside the outside the geothermal reservoir in order to be injecting more carbon dioxide with a smaller volume of water. Also, create some innovative methods to solidify the carbon dioxide underground. And vision is to extend our technology to more emission-intensive resources. If you attended CarbFix field trip yesterday, things probably is much clearer for you. In Iceland, you have cations in your reservoir, like calcium, magnesium, iron. And when you mix with water, with carbon dioxide, when it interacts with these cations, it turns into carbonate. Or if you enrich your water with H2S, when this water interact with calcium, magnesium, iron, it turns into sulfate. And in Iceland, you have abundant source of basalts, and you have right to say test. We can inject, and everything will be all right. But in New Zealand, our reservoirs doesn't have these cations in an abundant form. But we have this do-it-yourself attitude. So we are planning to inject some readily available materials in order to enhance these trapping mechanisms. We structured our our project under 4 groups. First is going to be examine. The second one is investigate. The third one is implement and integrate. And the fourth one is incorporate. In the examine, we are going to do everything in lab environment, in controlled environments, before we expand the technique to the large-scale field implementation. In the second investigate step, we are going to do more field-scale, large-scale implementation-related experimental work. In the implement and integrate, we are going to decide the material and set up, with the help of our industry partners, we are going to design a pilot plant to see its effect. And in the integrate, we are going to communicate with the indigenous people who are the owner of the resources, with stakeholders, with end users, with regional governments, and with scientific community. And we have been doing some modeling studies so far. We set up our laboratory, and we made a reactor which can handle high temperature pressure conditions in order to allow us to see the interactions and how is it going to behave when we inject carbon dioxide with other fluids within the rock. Then we do some two-dimensional or one-dimensional feed zone related numerical modeling as well. And later on, we switched into three-dimensional large-scale models. For example, this is a result from an experiment which is done by GNS for us, actually. We did last year, and at the time our laboratory wasn't ready. So we did the experiment, GNS had done the experiment for us. So they crushed the grey waki, which is a main base rock for the geothermal systems in New Zealand, and put into this reactor, which is 15 centimeter high, and they injected CO2 enriched water and CO2 and H2S enriched water from the bottom of the reactor. And in our simulations, we looked at how is it going to behave in terms of porosity, permeability, and what sort of minerals are going to be precipitating or dissolving. So most of the minerals, most of the reactions in the dissolution, so the dissolution is the dominant because CO2 decreases the pH and it creates some dissolutions, especially just around the injection point. We see much enrichment on the porosity and permeabilities. For example, for this case, if we had inject only brine, if we didn't include any carbon dioxide, the porosity and permeability was going to decrease a bit because of the minerals are inside the water brine was going to be precipitating. If we had inject NCG into the brine, the porosity and permeability was going to be increasing. And if we had used condensate instead of brine, permeability was going to be increasing much more. And while they are setting up those experiments, they collect samples, effluents every day. So we calibrate our model. So we have sense of reliability to our models because we calibrate it based on their daily samples. So we can do some history matching and we can rely on our models. But geothermal reservoirs are extremely complicated. So with 15 centimeter samples, it's impossible to characterize the reservoir. Especially this is from Natamariki, for example. This is the feed zone of Natamariki, and reactive surface area changes in 2 meters. This is enormous amount of change and also uncertainty. In order to address this, we decided to make larger scale models. And geothermal fields like Tehuka, Natamariki operators, they come and ask us, for example, for this case, they had 2 wells actually, and each of them had separate feed zones, and they wanted to know which one should be targeted actually. If we inject into which of them, we are going to have much more dissolution, or what sort of precipitation we are expecting. What is going to be the fate of our injected fluid? So we ran some one-dimensional feed zone models as well for Tehuka, and it also shows some dissolution. For this particular well, the injectivity was dropping with time, and according to our simulations, if we had injected a smaller amount of carbon dioxide, the injectivity wasn't going to be decreasing as much. And we can simulate in the long term what sort of minerals are going to be precipitating and dissolving. The models are quite explanatory to understand a little bit about the reactive surface areas and average, plus some interconnectedness between the wells, but still they are closed systems. The top of the models and the bottom of the models are closed, and it is homogeneous radially, so they are not really very representative to assess in the large-scale project-related risks. For example, when you inject your carbon dioxide, you want to know if it is going to support the reservoir pressure, if it is going to reach your production wells, if it is going to leak to the surface. So we need to know about them as well. So we gradually started to shift to 3-dimensional models. And first, in the 3-dimensional models, we need to have a stable model which can be utilized for predicting the effect of carbon dioxide injection. We wanted to create a stable model, and at the same time, it allowed us to see the evolution of a geothermal system, because while we are running our natural state models, we have to run it for hundreds of thousands of years to obtain a stable condition. So this allowed us to see how the geothermal systems form. We take your basalt, fresh, unaltered basalt, and put as a mineralogy. So this is the grid structure, that 3-dimensional grid structure we created. This is the aerial view, and this is the vertical grid structure. So we put some heat from underneath of the system, like this green area is normal terrestrial heat and the red one is a high temperature. So we put some higher heat flux under the mountain. This is our grid structure. We put some boundaries and deeper zones and reservoir and some ground lithology. And we run this system for 80,000 years, yes. And we can see how the system is evolving with time in this figure. If you look at on the left top, the system is heating, and you can see what's happening in 10,000 years, 20,000 years, now 30,000 years, and some of the minerals, primary minerals within the basalt are dissolving over the evolution of the geothermal reservoir. And what's happening in the secondary minerals, because some of the secondary minerals are forming in the meantime. So this shows how quartz and chalcedony and calcite, albite is precipitating over the time, and at the end of 80,000 years, what is their conditions. And after we obtain these stable conditions, our models are ready for running some experimental simulations to see what is going to be the effect of injection, carbon dioxide injection. For this case, we used rhyolite tuff instead of basalt, and this is the location of our production wells, the red ones. The blue one is injection location, injection of the brine, and the green one is the condensator injection. And these are the reinjection rates that we are injecting into our reservoir. And we can we can visualize, we can run different scenarios to see how much carbon dioxide we should include, what should be the distance between the wells, and what is the potential breakthrough, and what sort of fluid we should reinject. As a result, injected carbon dioxide may communicate and be produced with steam or two-phase fluids. This risk decreases the efficiency of the process. Sequestered carbon dioxide may still gradually release over time through the transport of reservoir fluid. The results of our model show that the carbon storage in geothermal reservoirs is feasible, so 99% has been stored in dissolved form. Mineralization in our type of geothermal systems wasn't really the case. However, when we enrich with these other cations and when we modify the pH, it was possible to obtain mineralization. Structural trapping was not observed because our amount of carbon dioxide wasn't so huge and it didn't release to the second phase. Thank you for your attention.
Thank you, Eileen. It's really interesting to hear how different New Zealand is compared to Iceland and how you can use our experience in your model. Yes, and now I would like to invite you all back to the stage, the speakers. Yes, we still have you all. Good. And I would like to open this Q&A session by asking them, each one of them, one question, and then I will open up questions from the audience. All right, so I want to start with you, Ken. Thank you for your presentation. It's really interesting to hear how air ingress can be so problematic and how you can measure it with these safety limits. And I'm really curious to know how many geothermal power plants do you know of that have actually experienced fires or explosions?
I know of roughly 6 that have experienced either fires or explosions, some both. Generally, those have all been without carbon capture, and due to the change in non-condensable gas content over time, along with possibly operating at different conditions. For example, if you turn down the rate of your plant low, the air ingress rate stays constant. And so then you change the ratio of air to fuel and can get into trouble. So roughly 6 for those reasons.
Okay, and can I ask you, are they all located in the US or all around the world?
Not just in the US.
Okay. But none in Iceland?
I'm not at liberty to say anything about
I am at liberty to
where
say
these are.
we have one of those cases at that.
Okay.
Yeah.
Thank you for interesting. Yeah, interesting. Eileen, I would like to ask you next. I was interested in your modeling and how you process with that. And I wanted to ask you if you can use the tough react model to model a full scale reservoir model. And what are the challenges of doing so? If you could please take the microphone. Yeah, thank you.
Yes, we can. We utilize tough react, so it interprets so it can use the space and time, and you can see how things are gradually changing. But it requires quite enormous amount of CPU power, computational power. So we had to use for these three-dimensional models maybe 20,000 CPU hours. So it's computationally quite demanding. Also, you can't really easily get a three-dimensional model from flow model from a field and implement the reactive transport, because you need a calibrated model which is in equilibrium. Also, you need to set up the natural state calibration again before you start to run your productions. So,
okay, perfect. Thank you. And next to you, Asa. I wanted to ask you, because you were talking about how you should interpret these CO2 emissions, and we have these gas fluctuations in the boreholes. How do you manage those in the bookkeeping of CO2 emissions?
So, in regards of the emission from the production, we sample the wells and also at the power plant, but the wells are where it's supposed to count, as it has sometimes decreases down to the power plant. So you have a little bit higher concentration next to the wells. But the wells are sampled once a year at least, depending on how they are fluctuating.
Okay, very good. Thank you. And next to you, Elin, I would like to ask you, because I saw you had a life cycle assessment of a power plant that's already up and running. I was just wondering if we can also use these life cycle assessment for new power plant operations, and how can we use them for us in advantage before we start?
Yes, we often do life cycle assessments after you have built a power plant or a building. But yes, as I mentioned in my talk, you can do these during your design phase, mm-hmm. or even before. And then you're maybe doing a more high-level study based on numbers from experience.
Yeah.
But yeah, or you could break it down and do like components of the design to compare. So okay. Yes, we could use them, and we should use them more in our design.
Yeah.
To make better decisions.
Okay, perfect. And finally to you, Sigurður. We were talking about how the oxygen is problematic, and I was just wondering how you monitor the oxygen level. How do you know if you have air ingress, like Ken was talking about?
Yeah, exactly. Well, first of all, I'd like to thank Ken for doing the safety talk. Regarding oxygen ingress, we monitor the O2 levels at our gas abatement plant, and we'll have a separate monitoring device in the new one in Silverstone. We also, when we have experienced an increase in O2 levels, we've usually sampled the NCGs from each individual turbine unit to help us narrow down the location. Yeah. but of course, as I think we'll hear from Ken's report, just not to leave everyone hanging, what we experienced in Hellisheiði was a fire within our NCG system last summer, which caused some damage, caused most probably by air ingress, obviously, of the gland steam leak off from one of our turbines. And I hope in the future we will go to a system where we have oxygen measurements on each turbine unit.
Yeah, exactly. Okay, thank you so much. Now if you guys could help me here, I want to open up the questions from the audience. So please just raise your hand if you have any questions. Oh, yep, Alexandra.
Hi, thank you so much for all your presentations. I have two questions, so one for Ása and one for Elín, because I'm very interested in the LCAs and have been doing some of these for a while also. So one for Ása, are you aware that there is some kind of consensus between countries how they choose to account for these natural or not natural emissions? For example, in Iceland, we do account for them. You account for all the emissions that come from your wells in the national inventory. And as I understand it, in, for example, Italy, they do not. Number two, Elín, the lifetime. So this is really interesting. We have such old stations now, a few of them that are older than 40 or 50 years. What does it mean? I'm sure you did sensitivity analyses. What does it mean in terms of the results for Svartsengi if we had to find a lifetime of 40, 50, 60, 70 years? Because they have many years ahead of them. And do you think there's a reason to make a larger lifetime definition, like for these studies in general, longer than 30 or 40 years, based on this experience?
Okay, so if we start with Ása, maybe you can hand her the other mic, Elín. Yep, thank you.
Very interesting question. In Italy, for example, there is an area called Amiata, and they emit 500 grams per kilowatt hour. That's like real numbers. And but that's only like less than 8% of what they emit from the area. So in that case, they interpret it like they say just, this is just part of the emission, this is just green energy, we don't have to account for the emission from production. So yeah, in New Zealand, there's another case, they just they account for everything, and if you emit more than 4,000 tons per year, then you have to account for it and pay. They have already started paying, and I think it's like $80 New Zealand dollars. Maybe.
It's fluctuating. Yeah, it was 60 to 90. It's changed.
Yeah.
But yeah, very interesting, a different approach, and it would be great if one would take a sensible line for everyone to do the same.
Yes, regarding the lifetime, thank you for the question. Because it was really interesting, and we had loads of discussion on it since Svartsengi was, even older than this 30-year lifetime limit that we were studying. We did a sensitivity analysis, and it showed the lifetime, the carbon footprint. Since we were only calculating the carbon footprint, it kind of was at a low. For Reykjanes, it was 60 years. I think it was a bit less for Svartsengi, but then it increased again. So you had to like optimize the energy production, like increase it again to make the carbon footprint lower. But with a longer lifetime, you have the problem of then you have to make a renewal of your machinery more often. And you have to include more maintenance and makeup wells, etc. So I don't know, but I think we could calculate for a longer, I think it would be more fair, so to speak, if we calculate for a longer, at least 50 or 60 years, rather than limit ourselves to 30.
Okay, thank you for this. Any more questions? We have one here. And maybe state your name and the company.
Yes, my name is Jón Ásgeirsson. I work for HS Orca. I have a question for Ásgeir regarding the reliability of surface measurements of CO2. If you walk through a geological field like on Reykjanes, you will see the topology is quite varied. You have cracks in some places and some not. Earthquakes that may release gases. And this is putting aside the weather, air pressure, etc., etc. So how reliable are really the surface measurements that you can do?
Another good question. Thank you for that. Yeah, complicated. So in our terms, we want to really do an aesthetic measurement now. So we would want to try to measure it continuously, the emission, to see how it varies over the year. If we can, you know, the Icelandic winter, they are not very approachable often. So yeah, the data is what it is. It is like it's a single point data that there's a great variant on the arrow bars there, and very complex. I would love to answer you better, but you know, but we want to do better in this field and do more sampling. And it would be of a great interest to do it, because we need to do this with all the sites, kind of, because they vary tremendously. You know, what the source is, what the conditions are in the site, clay, layers of clay, if it's very permeable. So yeah, it would be interesting to do like a similar approach in many sites. And see how to have the big picture on the natural emission.
Perfect, thank you. Any else? Yeah, we got one over there.
Hi, my name's Charlotte Barlow. I come from Aurora Energy Research, but it's more of an economics-based company, so this just comes from a geological interest, personal interest. The question is for ALEM and your experience modeling carbon mineralization in New Zealand. So really only in the conclusion of your presentation did you discuss the rhyolite composition of the host rock you were theoretically injecting in. So I wanted to ask you whether, I don't know enough about this, but whether the field in which you operate is mostly rhyolitic in composition, and you're kind of limited in that way to only testing in rhyolites. And also a follow-up on that is, given that you're capable of dissolving CO2 in your fluids, but unable to sequester it underground into minerals, do you really see this as an actual option in terms of sequestration in New Zealand, or do you foresee this as being infeasible? Thank you.
First of all, New Zealand's base rock is greywacke, but in the shallow zones there are ignimbrite and rhyolite zones. So we have options. We are not limited to rhyolite. It can be greywacke as well, but ignimbrite. But still, at the end of the day, they are not really having those cations in abundance form. So it is not really the easiest. Plus, in New Zealand, we need carbon dioxide because we are not really producing any, for the last 10 years, we are not allowed to drill any exploration well in New Zealand. And we close our refineries as well, and we desperately need food grade or clean carbon dioxide as well. So it is important. So there are lots of industrial suggestions to utilize carbon dioxide. But sometimes converting into calcite is also outside is also good an option. It can be used as a building materials. But if it's not necessary, that's create an opportunity to set up underground. Plus, according to our models, it's not really staying in the reservoir in solid form, but it is boosting the pressure of the reservoir because it's supporting, it increases the compressibility, it supports the reservoir pressure, so it increases, also it helps with the boiling point and enthalpy as well, so it increases the energy generation. So not only, I mean, our main target is not really dissolving in the precipitating in the solid form. Plus, sometimes when you inject carbon dioxide, it doesn't really scale just around your well. It goes and scale in the hotter zones. Calcite precipitates much better in the hotter zones. So it can create a sealed zone between the injection zone and production zone. So it can be helpful for decreasing the permeability and delaying the breakthrough as well.
Great, thank you.
Okay, thank you. Any further questions? We have 4 minutes left, so I'm going to ask Ken one more, if I may. I'm wondering, since flash plants may have issues with flammable gases, especially when capturing CO2, does that mean that binary plants are more preferable in the future?
That's an interesting question. Binary plants, if steam is coming out of the ground, then binary plants are more expensive and produce less energy per unit of fluid. So you could use a binary plant. You'd probably be better off paying for carbon capture and removing the oxygen and other species, in my opinion.
Okay.
So I don't think binary plants are going to be the only thing built in the future, if that's part of the question.
Mm-hmm. And any final question? No? Then I would just like to thank you all, and thank you for this great time management, and thank you all for these very interesting topics. I hope you all learned something here today, and at least I did, and I hope we can all fight together in the zero footprint geothermal. Thank you for the attendance, and hope you enjoy the rest of the conference.